am Sabu Joseph, Assistant Professor and Head of the Department of Aeronautical Engineering at ACE College of Engineering, Trivandrum. Today I would like to take a lecture on space technology, particularly that orbital maneuvers. We have to transfer some satellite from one orbit to another orbit. So for that purpose we have to give a lot of energy to reach that satellite into a higher energy orbit level. Here some classification I would like to view. See, orbital maneuver, it's three types. It's an impulse maneuver, Hoffman transfer, non-Hoffman transfer. In Hoffman transfer, further classified as elliptical and bi-elliptical transformation. And in Hoffman transfer is the most energy efficient transfer that we can. That means that we have to spend a minimum energy to transfer from one orbit to another orbit. Okay. Here, the energy of an orbit equal to minus mu by 2a. Mu is the gravitational parameter. It depends upon that any planets or anything is producing gravity. It depends upon that factor of the gravity. Okay, and A is the semi-major axis. Semi-major axis A. That means if that this is an on orbit 1 and it's another orbit 2, its semi-major radius is increasing compared to this one. That means energy level of the second orbit E2 is greater than E1 because here A2 is greater than A1. That means here it is increasing. Its quantity become reducing. That means it's a lesser negative. That means energy is increasing. And if A become infinity, that means its radius become infinity. It will cast into at infinity. This any particle or anything will cast into infinity. That means that any satellite or anything will follow that parabolic or hyperbolic trajectory, and it will go to infinity. That is the meaning of energy of a particular trajectory. Energy level of this trajectory. As I told you that that minimum energy consumption for one trajectory to another, we are following that Hoffman transfer. I am taking a figure for this one, whatever I have drawn here. Okay. For this, take this figure, and this is a trajectory, or this is an orbit 1, this is second orbit. I want to transfer a satellite or any spacecraft from point A to point B. We have to, that is that orbit A and orbit 1 and orbit 2 have that common focus, as it is indicated here. It's a common focus. And from the perihelion of this Hoffman transfer, we have to choose an Hoffman ellipse, Hoffman transfer ellipse. Okay, which is drawn with this orange color line, and this is the perigee position, this is apogee position. And from once that satellite or anything is revolving in a first orbit, we have to impart some energy, additional energy we have to give to them. For that purpose, we will be using some additional body of fuels in the rocket that will cause that increment in velocity. What increment velocity we can calculate it by? That is delta VA, which is equal to VA, velocity at elliptical, this Hoffman trajectory, velocity at A minus V1 will give you, this is that VA at this point. This VA, from this VA we can calculate how much energy is required to increase this much velocity by Shidowsky equation, that is delta V is equal to G naught ISP into Ln zeta. Zeta is the mass ratio of the rocket, and ISP is the specific impulse of the rocket, and G naught is a gravity acceleration due to gravity at some certain location where it starts from acceleration or anything. And once you know this mass ratio, you can find out how much propellant is burned. From there you can calculate what is the energy is we have imported to this Hoffman transfer. And once it is we have increased this delta V to this satellite or anything. This is that additional velocity required to follow this Hoffman elliptical trajectory. That means if you are only giving this delta V, this satellite will come to the point B and it will return to A. So if you want to keep that satellite in orbit 2, you have to give an additional energy from here to keep what is the energy of level of this orbit. For that you have to find out delta VB, which is equal to, that is velocity at 2 minus VB, velocity at B of this elliptical trajectory. And from this VB, we can again calculate by Shidowsky equation. We will get how much propellant is required to burn to keep that satellite in this second orbit, or orbit number 2. And some other parameters also we have to calculate. What is V1? V1 we can calculate from this equation, that is V is equal to V1 is equal to square root of mu by R1, and R1 is the radius of that first orbit, and V2 is equal to square root of mu by R2, where R2 is the radius of the second orbit. From this equations we can calculate V1 and V2. Remaining other terms are the VA. Again we have to calculate what is VA. For we have to calculate VA, it is an elliptical orbit, so we can use that orbital equation. R is equal to h square by mu into 1 by 1 plus E cos theta. Here is the eccentricity, which defines what type of this conic section it is in Hoffman ellipse. And h is the angular momentum, and mu is the gravitational parameter, and E is the eccentricity, which defines that what conic section is defined this Hoffman ellipse. And here we know theta is that anomaly. Anomaly is that inclination of angle somewhere else where that satellite or any planets or anything its angular position is defined. At this position A, theta becomes 0, and eccentricity you can calculate. E is equal to R2 minus R1 divided by R2 plus R1. R2 plus R1, and once you know eccentricity, you can calculate h at a Hoffman ellipse. H at Hoffman ellipse. Okay, once you know h, you can calculate the VA. VA is equal to h by RA. That is R1. Which is equal to h by R1. And VB also we can calculate. VB is equal to h by R2. From here you can calculate VB. From this we will get all the parameters, and we can calculate what is the delta VA, and delta VB is required. Therefore, the total velocity change required to keep that satellite from, we have to shift that satellite at orbit 1 to orbit 1 onto 2 is equal to delta VA plus delta VB will give this total change in velocity required to shift this satellite from orbit 1 to orbit 2. Similarly, and if you want to shift any satellite from higher energy level to lower energy level, you have to take out some energy from this satellite position in orbit 2 to orbit 2. The same way we can do that, the reverse way also we can do it. For that we have to calculate the same procedure, and a retro burning rocket system or opposite sense thrust producing system is required to keep that satellite into an initial orbit. And with this, I am concluding this lecture. Thank you for your time.